At the edge of a black hole, the universe seems to break its own rules. According to Einstein's equations, anything that crosses the event horizon is lost forever. Matter, light, even time itself. From the outside, it appears to vanish, erased from reality without a trace. But according to quantum physics, that should be impossible. In the quantum world, information cannot be destroyed. It can change form, become scrambled or hidden, but it can never truly disappear. If it did, the fundamental laws of physics would collapse. This contradiction is known as the black hole information paradox *, one of the deepest and most unsettling problems in modern science. In this documentary, we will explore what really happens to objects that fall into a black hole. We will examine why classical physics says information is lost, why quantum mechanics violently disagrees, and how this paradox has forced physicists to rethink the nature of space, time, and reality itself. We will follow the story from the first predictions of black holes, through Stephen Hawking's shocking discovery of black hole radiation, and into modern ideas involving holograms, quantum entanglement, and the structure of space-time at the smallest possible scales. Nothing here is science fiction. Every idea comes from real equations, real experiments, and decades of serious debate. If you enjoy calm, long-form explorations of the universe's deepest mysteries, consider subscribing to Theories Before Sleep for more documentaries like this. Now, let's begin at the point of no return and ask the question physicists still can't fully answer. Asterisks: when something falls into a black hole, does it truly disappear? For most of the 20th century, black holes were treated as a strange but relatively straightforward consequence of general relativity. They were regions of space-time where gravity became so intense that nothing, not even light, could escape once it crossed a boundary known as the event horizon. From the outside, a black hole was simple. It could be fully described by just a few properties: mass, electric charge, and rotation. This simplicity was not a coincidence. It was formalized in what physicists came to call the no-hair theorem *. According to this idea, black holes erase almost all details of the objects that form them or fall into them, no matter what you throw in: a star, a planet, a book, or an entire civilization. The black hole settles down into the same final state, indistinguishable from any other black hole with the same mass, charge, and spin. At first, this did not seem troubling. Classical physics had no problem with information being lost. If you burn a book, the story is gone. If you mix cream into coffee, you cannot recover the original pattern. Nature appeared to be full of irreversible processes, but this intuition was misleading. In the mid-20th century, physicists began to understand that at a fundamental level, the laws of nature behave very differently. Quantum mechanics introduced a radical constraint: information is conserved. The precise quantum state of a system always evolves in a reversible way. Even when things look chaotic or destroyed, the information is still there, hidden, scrambled, but not erased. This principle is not optional. It is built into the mathematics of quantum theory itself. If information were truly destroyed, quantum mechanics would stop making sense. Probabilities would no longer add up correctly. Cause and effect would become inconsistent. For decades, these two ideas, black holes and quantum information, existed side by side without conflict. Black holes belong to gravity, information belonged to quantum mechanics. The two domains rarely touched. That separation did not last. The first cracks appeared when physicists began asking a deceptively simple question: what happens to the information carried by an object that falls into a black hole? From the perspective of general relativity, the answer was clear. Once the object crosses the event horizon, it is gone forever. No signal can escape. No detail can be retrieved. The information describing the object is lost to the outside universe. From the perspective of quantum mechanics, that answer was unacceptable. If information disappears inside a black hole, then black holes are not just exotic objects. They are violations of the most fundamental rules of physics. At first, many physicists assumed the problem was philosophical rather than physical. After all, information falling into a black hole might still exist inside, even if it cannot be accessed. Perhaps the information is preserved somewhere deep in the black hole's interior. But this idea quickly ran into trouble. Black holes are not static. They are not eternal prisons. They evolve. In the 1970s, Stephen Hawking made a discovery that completely transformed the problem. By combining quantum mechanics with curved space-time, he showed that black holes are not truly black. They emit radiation. This radiation, now known as Hawking radiation, Hawking, arises from quantum effects near the event horizon. Over extremely long timescales, this radiation causes black holes to lose mass. Given enough time, a black hole will shrink and eventually disappear entirely. This was a shocking result. A black hole that evaporates leaves nothing behind, no remnant. No interior, no place for information to hide. If Hawking radiation is purely random, then when the black hole evaporates completely, all the information about what fell into it is gone forever. Not hidden, not scrambled, destroyed. This is the heart of the black hole information paradox. It is not merely a question about black holes. It is a question about whether the universe obeys its own laws. Hawking himself initially argued that information really is lost in black holes. He proposed that the universe is fundamentally non-unitary, that quantum mechanics breaks down in the presence of gravity. This was not a casual suggestion. It implied rewriting the foundations of physics. Many physicists were unwilling to accept this. If information can be destroyed in black holes, then quantum mechanics cannot be the ultimate theory of nature. Probability conservation fails, predictability breaks. The future no longer follows uniquely from the past. This would undermine not just black hole physics, but the entire structure of modern science. As a result, the black hole information paradox became one of the most intense debates in theoretical physics. It split the community into camps. Some believed information was truly lost. Others believed it must be preserved somehow, even if the mechanism was deeply hidden. What made the paradox especially disturbing was that both sides were supported by extremely solid reasoning. General relativity is extraordinarily well tested. Black holes are real astrophysical objects observed indirectly through gravitational waves and electromagnetic signals. Event horizons appear to exist. Quantum mechanics is even more successful. No experiment has ever shown information destruction at a fundamental level. Both theories work, both theories are trusted, but together they appear to contradict each other. This contradiction is not a technical glitch. It is a direct clash between the two pillars of modern physics. To understand why the paradox is so severe, it helps to think carefully about what information actually means in physics. Information is not just data in a human sense. It is the complete specification of a physical system's quantum state. If you know that state perfectly, you can in principle predict the system's future behavior exactly. When information is preserved, physics is deterministic at the deepest level, even if it appears random in practice. When information is destroyed, determinism breaks. The universe becomes fundamentally unpredictable. Black holes appear to sit right on this fault line. From far away, an object falling into a black hole seems to slow down, redshift and fade. Its signals stretch and weaken, never quite crossing the horizon from the observer's perspective. This led some physicists to argue that information is not lost, but merely frozen near the event horizon. But this argument fails once Hawking radiation is taken into account. Hawking radiation is thermal. It looks like random noise. It does not seem to carry detailed information about the black hole's interior. As the black hole evaporates, it emits radiation that appears completely uncorrelated with what fell in. If the radiation truly contains no information, then evaporation is a one-way erasure process. This conclusion was deeply unsettling. It suggested that black holes act like cosmic shredders of reality, places where the universe forgets its own past. Physicists were forced into an uncomfortable position. Either information is destroyed and quantum mechanics must be modified, or information is preserved and our understanding of black holes is incomplete. Both options are radical. For decades, there was no clear resolution. Calculations reinforced the paradox rather than dissolving it. Every attempt to track information seemed to confirm that it disappeared behind the horizon and never returned. The paradox became a kind of intellectual trap. The more carefully physicists analysed black holes, the more firmly the contradiction remained. And this is what makes the black hole information paradox so important. It is not a niche problem. It is a signal that our two best theories, general relativity and quantum mechanics, cannot both be complete in their current forms. Somewhere, something must give. In the next part, we will examine Stephen Hawking's original argument in more detail. We will look at how Hawking radiation is produced, why it appears thermal, and why this seemingly small quantum effect creates one of the largest crises in theoretical physics. Because once black holes can evaporate, the question becomes unavoidable. If the black hole disappears, what happens to everything that fell inside it? Stephen Hawking's argument for information loss did not rely on speculation or metaphor. It came from a concrete calculation grounded in quantum field theory and general relativity. To understand why the information paradox became unavoidable, it is necessary to look carefully at how Hawking radiation arises and why, at first glance, it seems incapable of carrying information. In empty space, quantum theory predicts that the vacuum is not truly empty. Instead, it is filled with constant microscopic fluctuations. Particle-antiparticle pairs briefly appear and annihilate each other everywhere, all the time. Under normal conditions, these pairs are virtual. They cannot be observed directly, and they leave no lasting trace. Near a black hole, this changes. The event horizon creates an extreme separation between regions of space-time. When a particle-antiparticle pair forms close enough to the horizon, it is possible for one particle to fall inward while the other escapes outward. From the perspective of a distant observer, it appears as though the black hole has emitted a particle. This is Hawking radiation. The escaping particles carry energy away from the black hole. Because energy and mass are equivalent, the black hole loses mass. Over incredibly long periods of time, this process causes the black hole to shrink. Crucially, Hawking's calculations showed that this radiation is thermal. Thermal radiation is random. It depends only on temperature, not on the detailed structure of the object emitting it. A hot iron bar emits thermal radiation, a star emits thermal radiation, and according to Hawking, a black hole emits thermal radiation as well. The temperature of a black hole depends only on its mass, charge, and spin. It does not depend on what fell into it. This was the fatal detail. If Hawking radiation is perfectly thermal, then it contains no information about the black hole's interior. Every emitted particle is statistically independent of the particles emitted before it. There are no hidden correlations encoding the past. As long as the black hole exists, one might imagine that information is still stored inside. But Hawking radiation ensures that the black hole does not exist forever. As evaporation continues, the black hole becomes smaller and hotter. The radiation intensifies. Eventually, the black hole reaches a point where semi-classical calculations break down and it disappears entirely. When that happens, there is nothing left. No interior region, no event horizon, no place for information to reside. The initial state of the universe before the black hole formed is not recoverable from the final state after evaporation. According to Hawking's original argument, many different initial states evolve into the same final state, a cloud of thermal radiation. This is the textbook definition of information loss. In quantum mechanics, this kind of evolution is forbidden. The mathematical framework of quantum theory requires that time evolution be unitary. Unitary evolution preserves information. It guarantees that the past can, in principle, be reconstructed from the present. Hawking's result violated unitarity. At first, Hawking believed this violation was real. He argued that gravity introduces a fundamental randomness into the universe. Black holes, in his view, genuinely destroy information. This position was radical but internally consistent. It required accepting that quantum mechanics is only an approximation, not a fundamental law. Many physicists found this unacceptable. Quantum mechanics had survived every experimental test ever performed. It underlies all of modern chemistry, electronics, and particle physics. To abandon it because of black holes felt like surrendering the most reliable theory in science. Others argued that Hawking's calculation must be missing something. The problem was that Hawking's calculation was extremely robust. It used standard quantum field theory in curved space-time. No obvious errors were found. Repeated analyses by different researchers confirmed the result. If Hawking radiation is truly thermal, information is lost. This led to an uncomfortable realization. The paradox could not be resolved by small corrections. It required a deep change in how black holes, space-time, or quantum mechanics are understood. One early idea was that information might escape in subtle correlations within Hawking radiation. Perhaps the radiation is not perfectly thermal. Perhaps tiny deviations accumulate over time and eventually encode the information. However, Hawking's original work showed that such correlations are exponentially suppressed. For large black holes, the radiation is extraordinarily close to perfect thermal noise. Any deviations would be far too small to carry the enormous amount of information stored in the black hole. Another proposal was that information might be preserved in a stable remnant left behind after evaporation. Maybe the black hole does not disappear entirely, but leaves a tiny object that stores the information. This idea created new problems. A remnant would need to store an arbitrarily large amount of information in an arbitrarily small volume. This leads to catastrophic instabilities. Remnants would be produced copiously in particle collisions, which is not observed. The remnant solution traded one paradox for another. Some physicists suggested that information escapes at the very end of evaporation, during the final explosive phase. But this would require the radiation emitted earlier to somehow know that information would be released later, violating causality. Others proposed that information remains inside the black hole forever, even after evaporation. But this implies that space-time itself must have hidden regions disconnected from the rest of the universe, which conflicts with standard notions of locality and energy conservation. Every simple escape route failed. The deeper physicists looked, the more rigid the paradox became. What made the situation even worse was that the paradox was not limited to exotic, speculative black holes. It applied to any black hole, including those formed by collapsing stars. If information is destroyed in black holes, then information is destroyed in realistic astrophysical processes. This meant the paradox was not confined to extreme theoretical limits. It affected the real universe. By the 1990s, the information paradox had become one of the central problems in theoretical physics. It was no longer just about black holes. It was about whether the universe is fundamentally predictable. The paradox also forced physicists to confront the meaning of space-time itself. Event horizons appeared to play a central role. They seem to be the boundary where information is lost. But event horizons are not physical objects. They are global features of space-time geometry. Their existence depends on the entire future evolution of space-time. This raised a troubling question. Could a purely geometric concept really destroy information? If so, then the laws of physics would depend on global space-time structure in a way that seemed deeply unnatural. As debates intensified, the paradox began to attract attention beyond black hole physics. It touched quantum information theory, thermodynamics, and even the philosophy of science. It became clear that resolving the paradox would require more than patching calculations. It would require a new understanding of how gravity and quantum mechanics coexist. One possibility was that space-time itself is not fundamental. Perhaps space-time emerges from deeper quantum degrees of freedom, and black holes are simply regions where that emergence behaves differently. Another possibility was that locality, the idea that information propagates only through nearby regions of space, breaks down near black holes. Both ideas were extreme, but the paradox left no gentle options. By the end of this stage of the debate, physicists were faced with a stark choice: either accept information loss and rewrite quantum mechanics, or accept that black holes behave in ways that defy classical space-time intuition. There was no third path that preserved everything. In the next part, we will see how this debate evolved as new ideas entered the picture. We will examine how string theory, holography, and quantum information began to suggest that information might not be lost after all, but preserved in a way that radically reshapes our understanding of reality. Because if information is not destroyed, then the black hole is not what it seems. It is not a cosmic eraser. It is something far stranger. As the debate over information loss intensified, it became increasingly clear that resolving the paradox would require ideas that went far beyond traditional black hole physics. The problem was not just technical, it was conceptual. It exposed deep assumptions about space-time, locality, and the nature of physical law itself. One of the first major shifts came from an unexpected direction: thermodynamics. Long before Hawking radiation was discovered, physicists had noticed something strange about black holes. They seemed to obey laws that closely resembled the laws of thermodynamics. Black holes had entropy proportional to the area of their event horizons. They had temperature once Hawking radiation was taken into account. They obeyed analogues of the first and second laws of thermodynamics. This resemblance was too precise to be a coincidence. Entropy is a measure of information. More precisely, it measures the number of microscopic configurations that correspond to the same macroscopic state. When entropy increases, information about microscopic details becomes harder to access. For ordinary systems, entropy is associated with volume. A gas in a box has entropy proportional to the number of particles and the space they occupy. Black holes were different. A black hole's entropy was proportional not to its volume but to the area of its event horizon. This was deeply counterintuitive. It suggested that the information content of a black hole is somehow encoded on its surface, not in its interior. This idea planted a seed. If black hole entropy counts microscopic states, then black holes must have an enormous number of internal degrees of freedom. Those degrees of freedom must store information. But where are they? Classical general relativity says the interior of a black hole is empty except for a singularity. There is no obvious place for microscopic states to live, yet the entropy formula demands they exist. This tension hinted that classical space-time might be hiding something. The next major development came from string theory. In the 1990s, string theorists succeeded in calculating the entropy of certain highly idealized black holes by counting microscopic quantum states. Remarkably, the result exactly matched the entropy predicted by black hole thermodynamics. This was a breakthrough. For the first time, black hole entropy was derived from an underlying quantum theory. It showed that black holes are not featureless objects. They have rich internal structure at the quantum level. More importantly, these microscopic states evolved according to standard quantum mechanics. Information was preserved. This did not immediately solve the information paradox, but it shifted the balance of evidence. It suggested that information loss was not inevitable. Instead, it hinted that Hawking's semi-classical calculation was incomplete. The question became, where is the missing information in Hawking radiation? The answer began to take shape through a radical idea known as the holographic principle. The holographic principle proposes that all the information contained within a volume of space can be described by degrees of freedom living on the boundary of that space. In this picture, the universe is like a hologram. A lower dimensional surface encodes a higher dimensional reality. This idea was inspired directly by black hole entropy. If black hole information scales with area, not volume, then perhaps space-time itself is fundamentally holographic. At first this sounded almost philosophical, but then it acquired mathematical precision. In the late 1990s, physicist Juan Maldacena proposed a concrete realization of holography known as the AD/CFT correspondence. It showed that a theory of gravity in a higher dimensional space-time is exactly equivalent to a quantum field theory without gravity living on its boundary. Crucially, the boundary theory is manifestly unitary. Information is never lost. If black holes exist in the gravitational theory, their evolution must be mirrored by a unitary process in the boundary theory. Information cannot disappear. This result sent shockwaves through theoretical physics. It strongly suggested that black hole evaporation is fundamentally information preserving, even if the mechanism is not obvious from the perspective of classical space-time. In this framework, the event horizon is no longer a one-way membrane that destroys information. Instead, it becomes a region where information is scrambled and encoded in subtle correlations. From the outside, Hawking radiation still looks thermal at first, but over time, correlations develop between the emitted particles. These correlations are incredibly complex, but they are there. This idea led to the concept of the Page curve. Don Page argued that if black hole evaporation is unitary, then the entropy of the radiation should follow a specific pattern. Initially, the entropy increases as radiation is emitted, but after a certain point, now called the Page time, the entropy begins to decrease as information flows out. This behavior is impossible if the radiation is purely thermal. For decades, the Page curve was a theoretical prediction without direct proof. The calculations required full control over quantum gravity, which seemed out of reach. Yet the idea reshaped how physicists thought about the paradox. It reframed the problem. Instead of asking whether information is lost, the question became how information escapes. This shift had profound consequences. It implied that black holes are not simple objects governed solely by classical geometry. They are quantum systems with an enormous number of degrees of freedom. Their behavior cannot be fully captured by semi-classical approximations. It also implied that space-time itself may not be fundamental. The smooth geometry described by general relativity might emerge from deeper quantum processes, just as temperature emerges from microscopic particle motion. In this picture, the event horizon is not a sharp boundary where physics breaks down. It is an emergent feature, valid only at large scales. At the microscopic level, information is never lost, it is redistributed. However, this raised a new problem. If information escapes in Hawking radiation, how does it do so without violating locality? Information cannot travel faster than light. It cannot jump from inside the horizon to the outside without crossing the horizon. Yet unitarity demands that it must. This tension led to one of the most controversial developments in the history of the paradox, the firewall argument. Some physicists propose that the event horizon is not smooth after all. Instead, it might be a violent region filled with high-energy particles, a firewall that destroys anything falling in. This would allow information to escape, but at the cost of violating the equivalence principle, one of the core ideas of general relativity. The firewall proposal was deeply unsettling. It suggested that an infalling observer would be incinerated at the horizon, contradicting decades of theoretical expectation. It forced physicists to choose between preserving unitarity and preserving the smoothness of space-time. Once again, there was no comfortable option. The information paradox had evolved. It was no longer just about whether information is lost. It was about which cherished principles of physics must be sacrificed: locality, equivalence, unitarity. At least one of them appeared to be incomplete. In the next part, we will explore this crisis in more detail. We will examine the firewall paradox, the role of quantum entanglement, and why resolving the information paradox may require a radical rethinking of what space-time actually is. Because by this point, it has become clear that black holes are not just cosmic objects, they are laboratories for the deepest questions about reality itself. As the implications of holography and unitarity became harder to ignore, the black hole information paradox entered its most volatile phase. The question was no longer whether information is preserved in principle, but how that preservation could coexist with everything else we thought we understood about space-time. At the center of this crisis was a fragile balance between three principles that had never before been forced into direct conflict. The first was unitarity, the quantum mechanical rule that information is never destroyed. The second was locality, the idea that information cannot propagate faster than light or jump across space-time discontinuously. The third was the equivalence principle, the cornerstone of general relativity, stating that a freely falling observer should experience smooth space-time at the event horizon. For decades, physicists assumed these principles were mutually compatible. The black hole information paradox revealed that they might not be. The conflict crystallized through a careful analysis of quantum entanglement. Hawking radiation is created in entangled pairs. One particle escapes to infinity while its partner falls into the black hole. This entanglement is essential to the thermal nature of the radiation. Each outgoing particle is entangled with something inside the horizon. However, if information is to escape in the radiation, later Hawking particles must be entangled with earlier ones. This is required by unitarity. The radiation must gradually encode correlations that reconstruct the original information, but quantum mechanics forbids a particle from being maximally entangled with two independent systems at once. This is known as the monogamy of entanglement. Here lies the contradiction. An outgoing Hawking particle cannot be fully entangled both with its interior partner and with the earlier radiation. One of those entanglements must break. If the entanglement with the interior breaks, the event horizon becomes a region of violent quantum effects. The smoothness of space-time fails. A firewall forms. If the entanglement with the radiation fails, information cannot escape. Unitarity fails. There is no third option. This realization led to the firewall paradox proposed in 2012. It was not a speculative idea. It was a logical consequence of trying to preserve all known principles at once. The firewall argument sent shockwaves through the physics community. The equivalence principle had been tested experimentally to extraordinary precision. It was one of the most trusted ideas in physics. To abandon it at the event horizon seemed extreme, but abandoning unitarity seemed even worse. It would mean rewriting quantum mechanics itself. Locality too appeared sacred. Without it, causality becomes ambiguous. Yet the paradox suggested that at least one of these principles must be modified or reinterpreted. The debate quickly became intense. Some physicists argued that the firewall must exist. They accepted that the horizon is not smooth and that an infalling observer would encounter extreme physics. This preserved unitarity and locality but violated the equivalence principle. Others argued that firewalls are unacceptable. They proposed that locality breaks down in subtle, non-obvious ways near black holes. Information might escape through non-local quantum effects that do not allow faster-than-light signaling but still violate naive notions of space-time separation. This idea was uncomfortable but not unprecedented. Quantum mechanics already contains non-local correlations through entanglement. Perhaps gravity amplifies these effects in extreme conditions. A third camp argued that semi-classical reasoning simply cannot be trusted near black holes. Hawking's calculation, though mathematically sound, might be missing essential quantum gravitational corrections. The paradox might dissolve once a complete theory of quantum gravity is available. This position was cautious but frustrating. It offered no concrete mechanism, only the promise of future understanding. What became clear was that black holes were exposing the limits of current frameworks. They were forcing physicists to confront the possibility that space-time is not fundamental. If space-time emerges from quantum entanglement, then horizons, locality, and even geometry itself may be approximate concepts. They may break down in subtle ways without obvious observational signatures. This idea gained traction through a surprising connection between geometry and entanglement. In holographic theories, the structure of space-time appears to be determined by patterns of quantum entanglement in the underlying quantum system. Regions of space-time that are strongly entangled appear close together geometrically. Regions that are weakly entangled appear far apart. From this perspective, space-time is not a background stage, it is a manifestation of quantum information. If this is true, then black holes are not holes in space-time. They are regions where entanglement is reorganized in extreme ways. The firewall paradox then becomes a question about how entanglement is redistributed during evaporation. The horizon's smoothness depends on specific entanglement patterns. If those patterns change, smoothness may fail. This reframing softened the paradox without fully resolving it. It suggested that the problem lies not in destroying information, but in assuming that space-time remains classical at the horizon while information escapes. Perhaps the horizon is smooth for infalling observers only under certain conditions. Perhaps the smoothness is approximate, not exact. These ideas challenge deeply held intuitions. For an outside observer, a black hole behaves like a hot quantum system that slowly leaks information. For an infalling observer, space-time appears normal, at least initially. Reconciling these two perspectives may require abandoning the idea that there is a single observer-independent description of reality. This led to the principle of black hole complementarity. According to complementarity, there is no contradiction, because no observer can see both sides of the paradox. An outside observer sees information encoded in Hawking radiation. An infalling observer sees information fall smoothly through the horizon. Both descriptions are valid within their own domains, but they cannot be combined into a single global picture. Complementarity preserves unitarity in the equivalence principle, but it sacrifices naive realism. It suggests that reality may depend on the observer in a fundamental way. This idea was controversial but influential. It hinted that the paradox arises from insisting on a global description that nature does not allow. However, complementarity itself came under pressure from the firewall argument. The monogamy of entanglement seemed to invalidate simple complementarity. Once again, the paradox refused to disappear. By this stage, it was clear that black holes were not merely astrophysical objects. They were forcing a re-examination of what it means for physical laws to be consistent. The paradox was no longer localized to the event horizon, it extended into the foundations of quantum theory, space-time, and information itself. Physicists began to suspect that the resolution would not look like a traditional solution. It would not simply fix a calculation or add a missing term. It would require rethinking the conceptual architecture of physics. In the next part, we will explore how recent breakthroughs in quantum information theory and gravitational path integrals have provided new tools to attack the paradox. These developments have led to concrete calculations that reproduce the page curve and suggest a way forward. For the first time in decades, the paradox may be approaching a resolution. But that resolution comes at a surprising cost. It forces us to accept that the universe may store information in ways that defy classical intuition, ways that blur the boundary between inside and outside, between geometry and data, and between what exists and what can be known. The turning point in the black hole information paradox did not come from a dramatic new physical principle, but from a careful re-examination of what calculations were actually allowed in quantum gravity. For decades, physicists had debated the paradox largely at a conceptual level, because the tools required to compute information flow in evaporating black holes simply did not exist. That began to change in the late 2010s. The breakthrough came from an unexpected source: gravitational path integrals and quantum information theory. These tools allowed physicists to ask a very precise question that had previously been out of reach. Can one explicitly calculate the entropy of Hawking radiation in a theory that includes quantum gravity effects? This question mattered because of the page curve. As discussed earlier, Don Page predicted that if black hole evaporation is unitary, the entropy of the emitted radiation should follow a specific trajectory. Early in the evaporation process, the radiation entropy increases because the radiation appears thermal and uncorrelated. After roughly half the black hole's entropy has been emitted, the curve should turn around. The radiation should begin to purify itself as information escapes, eventually returning to zero entropy when the black hole is gone. For decades, this curve was a theoretical expectation with no direct derivation. Hawking's original calculation produced only the rising part of the curve. It predicted ever-increasing entropy, ending in total information loss. The question was whether a more complete calculation, one that properly included quantum gravitational effects, would reproduce the full page curve. In 2019, physicists achieved exactly that. Using semi-classical gravity combined with replica trick techniques from quantum information theory, researchers computed the entropy of Hawking radiation in simplified models of black holes. The results were shocking. The calculations produced the page curve. This was not a philosophical argument. It was a concrete mathematical result. The entropy of the radiation increased at first, then decreased, exactly as expected for a unitary process. The implication was unavoidable. Information is not lost in black hole evaporation. Hawking's original conclusion, though brilliant and internally consistent, was incomplete. His calculation had missed non-perturbative contributions from space-time geometries that were previously neglected. These contributions came from what are now called quantum extremal surfaces and replica wormholes. To understand why this mattered, it is important to grasp what was missing from earlier calculations. Hawking treated the space-time outside the black hole as a fixed background. He calculated quantum fields on that background and ignored the back reaction of quantum information itself on geometry. This approximation is extremely accurate for many purposes, but it fails when questions of information and entropy are involved. Entropy is not just a property of matter. In gravity, it is deeply tied to geometry. The new calculations allowed space-time itself to fluctuate in subtle ways that were previously excluded. When these fluctuations were included, entirely new contributions to the radiation entropy appeared. These contributions effectively connected the radiation outside the black hole to regions inside it through non-trivial space-time topologies. These connections did not allow signals to travel faster than light. They did not violate causality in any obvious way, but they changed how information was counted. The result was that information stored inside the black hole became encoded in the radiation through extremely subtle correlations. These correlations are invisible at early times, which is why Hawking radiation appears thermal, but they grow over time and eventually dominate. This resolved the paradox at a technical level. Black hole evaporation is unitary, information is preserved. Yet this resolution raised new questions that were just as profound. If information escapes through subtle correlations in Hawking radiation, how is this compatible with the smoothness of space-time at the horizon? How do these correlations form without violating locality? And what do replica wormholes actually mean physically? Replica wormholes are not ordinary tunnels through space-time. They are mathematical objects that arise when computing entropy using replicated geometries. Their physical interpretation is subtle and still debated. What is clear is that they imply space-time is more flexible than previously assumed. The geometry relevant for computing entropy is not the same as the geometry experienced by a classical observer. This reinforces a key lesson of the paradox. Space-time is not fundamental. It emerges from underlying quantum degrees of freedom, and its behavior depends on what is being measured. Questions about information probe space-time in a different way than questions about motion or energy. The new calculations also clarified why the paradox was so difficult to resolve. The missing physics was not local. It involved global properties of space-time and entanglement that cannot be captured by semi-classical reasoning alone. Hawking was not wrong. He was incomplete. This distinction matters deeply. It shows that even the most careful reasoning can fail when applied beyond its domain of validity. It also shows that resolving paradoxes does not always require abandoning cherished principles. Sometimes it requires understanding how those principles are realized in a deeper framework. The success of the page curve calculation strongly suggests that unitarity is preserved. Information is not destroyed. The universe remains fundamentally predictable. But this success does not restore the classical picture of black holes. Instead, it replaces it with something stranger. In the new picture, information is not stored neatly inside the black hole. It is distributed across space-time in a highly non-local way. The distinction between inside and outside becomes blurred when quantum effects are taken seriously. This has dramatic consequences for how we think about the event horizon. The horizon is no longer a sharp boundary separating two independent regions. It is an emergent concept that depends on the observer and the scale at which physics is described. From a classical perspective, the horizon is real and absolute. From a quantum informational perspective, it is porous in a subtle, non-classical way. This does not mean that observers can see inside black holes or retrieve information at will. The correlations that encode information are extraordinarily complex and inaccessible in practice, but they exist, and their existence is enough to preserve the consistency of physics. The resolution of the information paradox also reshapes the firewall debate. If information escapes through correlations that involve the entire space-time geometry, then the monogamy of entanglement constraints may be satisfied without requiring a violent horizon. The entanglement structure is more intricate than the simplified models assumed. This suggests that the horizon may remain smooth after all, at least in a qualified sense. However, the story is not over. The calculations that reproduce the page curve are performed in simplified models, often involving lower dimensional gravity or idealized black holes. Extending these results to realistic four-dimensional black holes remains an active area of research. Moreover, the physical interpretation of replica wormholes is still unclear. Do they represent actual space-time connections? Or are they merely accounting devices in the mathematics of entropy? These questions are not cosmetic. They go to the heart of what space-time is. The paradox has not been eliminated, it has been transformed. Instead of asking whether information is lost, physicists now ask how space-time organizes information. Instead of treating geometry as primary, they treat quantum entanglement as fundamental. This is a profound shift. It suggests that reality is built not from points in space, but from relationships between quantum degrees of freedom. Geometry emerges from information, not the other way around. Black holes in this view are not places where physics breaks. They are places where the underlying structure of reality becomes visible. They expose the scaffolding beneath space-time. In the next part, we will explore the philosophical and physical implications of this shift. We will examine what it means for causality, observation, and the nature of existence itself when information takes precedence over geometry. Because resolving the black hole information paradox does not return us to a comfortable universe. It leaves us with a deeper, stranger one, where space, time, and matter are secondary to something far more abstract and far more fundamental. With the technical resolution of the black hole information paradox taking shape, physics did not return to stability. Instead, it entered a more unsettling phase. The paradox had been softened mathematically, but its conceptual consequences were impossible to ignore. Preserving information required a fundamental reordering of what was considered basic in the universe. The most important shift was this. Asterisk information appeared to be more fundamental than space-time itself. For centuries, physics treated space and time as the stage on which reality unfolds. Even after Einstein, space-time remained the primary structure, flexible but real. Matter moved through it. Fields lived on it. Events were ordered by it. The information paradox undermined this hierarchy. If black hole evaporation preserves information, then the geometry of space-time must adjust itself to protect that information. This means geometry cannot be the deepest layer of reality. It must be emergent, an effective description that arises from something more fundamental. That something appears to be quantum entanglement. In modern theoretical physics, entanglement is no longer viewed as a strange side effect of quantum mechanics. It is increasingly treated as the glue that holds space-time together. The connections between quantum degrees of freedom determine how space is stitched into a coherent whole. In this picture, distance is not primary, correlation is. Two regions of space appear close because their underlying quantum states are strongly entangled. Regions appear far apart because their entanglement is weak. Geometry becomes a map of informational relationships. Black holes push this idea to its extreme. A black hole is a region where entanglement is reorganized violently. Information is not destroyed, but it is redistributed across degrees of freedom that no longer resemble classical space. From the outside, this redistribution looks like loss. From the deeper level, it is preservation through complexity. This perspective explains why Hawking radiation looks thermal. Thermal behavior is what information looks like when it is maximally scrambled. The radiation does not forget the past. It hides it in correlations that are astronomically difficult to decode. In principle, the information is there. In practice, it is unreachable. This distinction matters. Physics does not require information to be recoverable by observers. It only requires that information is preserved by the laws of nature. A book burned to ashes still has its information encoded in molecular motions, even if no one can reconstruct the text. Black holes appear to do something similar, but at a cosmic scale. This realization reframes the original intuition that black holes destroy things. They do not erase, they transform. The information paradox also forces a reconsideration of causality. If information escapes a black hole without violating relativity, then causality must be respected in a non-classical way. Information does not travel through space-time in the usual sense. It is reorganized across the quantum state of the universe. This sounds abstract, but it has precise meaning. In holographic descriptions, information about the interior of a black hole is encoded in degrees of freedom that live far away on the boundary of space-time. The encoding is non-local. No single point contains the information. Only the full quantum state does. This means that asking, "Where is the information?" may be the wrong question. The correct question is, how is the information encoded? Once phrased this way, many classical paradoxes dissolve. The interior of the black hole is not a separate region that must communicate with the exterior. Both interior and exterior descriptions emerge from the same underlying quantum state. The apparent contradiction arises only if we insist on treating space-time as fundamental. This has deep implications for observation. An infalling observer experiences smooth space-time and crosses the horizon without drama. An outside observer sees information slowly leak out in radiation. These two descriptions are not contradictory because they are not describing the same level of reality. They are complementary perspectives on an underlying quantum structure. This idea challenges classical realism. It suggests that there may not be a single global description of reality that applies to all observers simultaneously. Instead, reality may be layered, with different descriptions valid in different contexts. This is not unfamiliar in physics. Wave-particle duality already taught us that mutually incompatible descriptions can both be true. Black holes extend this lesson to space-time itself. The resolution of the information paradox also reshapes the concept of entropy. Entropy is no longer merely a measure of disorder, it becomes a measure of entanglement. Black hole entropy counts how entangled the black hole is with the rest of the universe. As the black hole evaporates, that entanglement is transferred to the radiation. The page curve reflects this transfer. Entropy rises as entanglement builds, then falls as information is released. This picture unifies thermodynamics, quantum mechanics, and gravity in a single framework, but it comes at a cost. It forces us to abandon the idea that space-time is fundamental and observer-independent. It suggests that geometry itself is a derived concept, meaningful only in certain limits. This is deeply unsettling, because space-time is the most immediate aspect of reality we experience. To say it is emergent feels like saying the ground beneath us is an illusion. Yet this is where the mathematics leads. The information paradox has become one of the strongest arguments that space-time is not the foundation of reality. It is a macroscopic approximation, like temperature or pressure, useful, real, but not fundamental. At the fundamental level, the universe may be a vast quantum system whose primary features are entanglement and information flow. Black holes are not holes in this system. They are regions where the encoding becomes maximally dense. This perspective also reshapes the meaning of the singularity. In classical general relativity, the singularity is a point where space-time curvature becomes infinite and physics breaks down. In a quantum informational view, the singularity may not be a physical point at all. It may simply mark the breakdown of the space-time description. The true physics continues beyond it, but not in space-time terms. This does not mean singularities are harmless. It means they are indicators that a different description is required. The information paradox thus acts as a guidepost. It tells us where our intuitions fail and where new principles must apply. It also explains why black holes have become central to so many areas of theoretical physics. They are not special because they are rare or exotic. They are special because they compress all fundamental issues into a single object. In a black hole, gravity is strong. Quantum effects are unavoidable. One of its thermodynamics is exact. Information is at stake. Few systems force so many principles into conflict at once. The progress made in resolving the paradox has also influenced other fields. Ideas about entanglement and geometry now appear in discussions of quantum error correction, condensed matter physics, and even the nature of time. The black hole has become a Rosetta Stone for modern physics. Yet despite all this progress, something important remains unresolved. While information may be preserved globally, the experience of observers remains puzzling. What does an infalling observer actually experience? Is the horizon truly smooth? Does space-time remain classical all the way down? These questions are not yet answered. The new calculations suggest that space-time remains smooth in many cases, but they do not prove it universally. The firewall debate has not been fully settled. It has been reframed, not eliminated. This leaves us in a strange position. The laws of physics appear to be consistent. Information is preserved. The paradox is technically resolved, but the intuitive picture of black holes has been permanently altered. They are no longer cosmic trash bins where things disappear. They are dynamic quantum systems that redistribute information in ways that defy classical intuition. They are not places where reality ends. They are places where the structure of reality is revealed. In the next part, we will explore what all of this means for time, causality, and the future of physics. Because if space-time is emergent and information is fundamental, then the universe is not what it appears to be at first glance, and black holes are the clearest evidence we have of that fact. As the black hole information paradox moves beyond its technical resolution, it begins to reshape ideas that once seemed untouchable. Among the most affected is the concept of time itself. Black holes force physics to confront time not as a smooth universal flow, but as an emergent feature tied to information and entanglement. In classical physics, time is absolute. In relativity, it becomes flexible but still fundamental. Events are ordered along world lines, and causality is preserved by the structure of space-time. Even when space-time bends or stretches, time remains a core ingredient of reality. The information paradox challenges this assumption. If space-time emerges from quantum entanglement, then time may also emerge from deeper informational processes. It may not exist as a fundamental dimension, but as a way of organizing changes in quantum correlations. Black holes make this idea unavoidable because they scramble information at the fastest rate allowed by physics. They are the most efficient information mixers in the universe. This scrambling is not random destruction. It is a precise unitary evolution that spreads information across degrees of freedom until it becomes inaccessible in practice. From this perspective, time inside and outside a black hole is not the same phenomenon. For an external observer, the black hole evolves slowly. Its evaporation takes immense periods of time. For an infalling observer, crossing the horizon happens in finite proper time, with no immediate indication that anything extraordinary has occurred. Both descriptions are correct within their own frameworks, but they cannot be combined into a single objective timeline. This forces a re-evaluation of what time actually measures. Instead of being a universal parameter, time may be a bookkeeping device that tracks how information changes relative to a given observer. In quantum systems, time is often treated this way. It is not an operator like position or momentum. It is an external parameter that orders evolution. In gravitational systems, that ordering becomes observer dependent. Black holes amplify this effect. They create regions where the flow of time diverges dramatically between observers. This divergence is not just geometric, it reflects how information is processed and distributed. The evaporation of a black hole is an information theoretic process. It is not simply matter leaking away. It is a gradual reorganization of entanglement between the black hole and the rest of the universe. As entanglement shifts, entropy changes. As entropy changes, the effective arrow of time emerges. This suggests that the arrow of time is not fundamental either. It arises from how information spreads and becomes inaccessible. Black holes sit at the extreme end of this process. They begin in a low entropy state when they form and evolve toward higher entropy as they interact with their environment. Their evaporation reverses this process in a subtle way, transferring entropy to the radiation. The page curve is not just a statement about information, it is a statement about time. It tells us that the direction of time, as experienced by the universe, is linked to the flow of entanglement. This insight connects black holes to a much broader question: why does time have a direction at all? In fundamental physics, most equations are time reversal symmetric. They work equally well forward and backward. The arrow of time arises not from the laws themselves, but from boundary conditions and entropy. Black holes provide a laboratory where this abstract idea becomes concrete. The information paradox forced physicists to track entropy and entanglement with unprecedented precision. In doing so, it revealed that time's arrow is deeply tied to information flow. This realization also reframes causality. Causality is usually understood as the rule that causes precede effects. In space-time, this is enforced by light cones, but in quantum systems, causality is more subtle. Correlations can exist without direct causal influence. Black holes operate at the boundary between these regimes. Information escaping in Hawking radiation does not violate causality because it does not transmit usable signals faster than light. The correlations that encode information are non-local, but they do not allow communication. This distinction is crucial. It shows that causality can survive even when locality is weakened. The universe remains consistent, but our classical intuitions about space and time must be updated. This has implications far beyond black holes. If space-time and time itself emerge from entanglement, then the early universe may not have had a well-defined time direction. Inflation, cosmic expansion, and the growth of structure may all be manifestations of information dynamics rather than purely geometric evolution. Black holes thus become windows into the origin of time. They show how a system can have different temporal descriptions depending on perspective, without contradiction. They demonstrate that time is not a universal backdrop, but a relational concept. This challenges deeply ingrained assumptions. It suggests that asking what happens inside a black hole may be the wrong question. Inside and outside are space-time notions that lose meaning at the fundamental level. The more relevant question is how information is encoded and transformed. From this viewpoint, the black hole interior is not a place. It is a pattern in the quantum state. This idea sounds abstract, but it has concrete consequences. It explains why attempts to locate information spatially fail. It also explains why paradoxes arise when we insist on classical geometry. The information paradox is not a contradiction in nature, it is a contradiction in our language. We are using space-time concepts to describe processes that are fundamentally informational. Once this is recognized, many puzzles soften. The horizon is no longer a rigid surface, it is a feature that emerges in certain descriptions. The singularity is not a physical endpoint, it is the breakdown of a particular coordinate system. Even the notion of disappearance must be reinterpreted. Objects falling into black holes do not vanish. They become encoded in a way that no longer resembles objects. Their identity dissolves into correlations. This is not annihilation. It is transformation. The universe does not forget. It reorganizes. This realization also alters how we think about determinism. If information is preserved globally, then the universe remains deterministic at the deepest level. But determinism does not imply predictability. Black holes demonstrate this distinction clearly. In principle, the information about everything that falls into a black hole is preserved in the Hawking radiation. In practice, extracting that information would require decoding correlations of unimaginable complexity. The laws are deterministic. The outcomes are effectively unpredictable. This reconciles two seemingly opposing views, a lawful universe and an uncertain experience. The information paradox thus resolves into a more subtle picture of reality, one where fundamental order coexists with practical unpredictability. As these ideas mature, they are influencing how physicists think about other extreme systems, from the early universe to quantum computers. The techniques developed to study black holes are now applied to questions about error correction, complexity, and the limits of computation. Black holes have become theoretical testing grounds for ideas that reach far beyond astrophysics. Yet despite all this progress, one question remains emotionally powerful. What happens to an object that falls into a black hole? From the outside, it appears to fade, stretch, and disappear. From the inside, it continues its journey without noticing anything special at the horizon. From the deepest level, it dissolves into information that is redistributed across the universe. None of these descriptions are wrong. They are layers. The information paradox taught physics how to accept layered descriptions without demanding a single, absolute narrative. In the next part, we will explore what this layered view of reality means for observation, measurement, and the limits of scientific knowledge. Because if reality itself is layered, then knowing it may require abandoning the idea that there is always a single final answer. Black holes are not just objects that challenge physics, they are mirrors reflecting the limits of how we understand existence itself. As the implications of the black hole information paradox spread outward, they began to influence not only how physicists think about space-time and time, but also how they think about astronomical observation itself. Black holes force an uncomfortable realization. What can be observed, what exists, and what can be known are not always the same thing. In classical physics, these ideas are closely aligned. If something exists, it can in principle be observed. If it can be observed, it can be known. Measurement reveals reality. Black holes break this alignment. An object falling into a black hole continues to exist in a perfectly valid physical sense. Its information is preserved. The laws of physics still apply to it. Yet for an outside observer, that object becomes permanently inaccessible in any ordinary way. This is not just a practical limitation, it is a structural one. The event horizon does not merely block signals, it divides the universe into regions with different informational access. What happens beyond the horizon cannot be directly observed, yet it still influences the global quantum state of the universe. This forces physics to distinguish between asterisk ontological existences and asterisk operational accessibility. Something can exist without being observable. Something can be knowable in principle without being knowable in practice. The information paradox lives precisely in this gap. For an external observer, all information about the infalling object must eventually be encoded in Hawking radiation, but this encoding is so complex that no realistic observer could ever decode it. The radiation is not labelled, it is not organised. It is spread across astronomical numbers of particles, each carrying minuscule correlations. This means that information is preserved globally, but effectively lost locally. Physics must therefore accept a layered notion of knowledge. There is what the universe knows, and there is what the observers can know. Black holes make this distinction unavoidable. This realization reshapes the role of measurement in quantum mechanics. In ordinary quantum systems, measurement plays a central role. Observing a system collapses its wave function, producing a definite outcome. Information becomes classical. But black holes complicate this picture. When an object falls into a black hole, no observer can perform a measurement that captures its full quantum state afterward. The system becomes effectively unmeasurable, not because it violates quantum mechanics, but because it exceeds the capacity of any observer. This pushes quantum theory into a new regime, one where unitarity holds globally, but classical outcomes become observer-dependent. From the outside, the black hole behaves like a thermal object. From the inside, it behaves like empty space until tidal forces grow strong. From the deepest level, it is neither. It is a highly entangled quantum system. Each description is incomplete on its own. This layered structure of description is not a failure. It is a feature of a universe where information is fundamental and space-time is emergent. The information paradox thus teaches physics how to live with contextual truth. Truth is not abandoned, but it is no longer absolute in a classical sense. Statements about reality must specify the framework in which they apply. This is uncomfortable because it clashes with the intuition that there is one objective story of what happens. Black holes suggest that there may be multiple consistent stories, each valid within its own domain, none of which can be elevated to a universal narrative. This idea extends naturally to the question of observation and experiment. Can the black hole information paradox ever be tested? In a direct sense, probably not. The timescales involved in black hole evaporation are far beyond any conceivable experiment. The decoding of Hawking radiation is computationally infeasible even in principle for large black holes, yet the paradox has already been tested indirectly. Its resolution relies on the internal consistency of quantum mechanics, thermodynamics and gravity, the success of holographic models, the reproduction of the Page curve, and the coherence of quantum gravity frameworks provide indirect evidence that information preservation is real. In this way, the paradox reshapes what counts as evidence in fundamental physics. It shows that not all validation comes from direct observation. Some comes from consistency across independent theoretical structures. This is not unprecedented. Many aspects of particle physics were accepted long before direct experimental confirmation because they were required for theoretical coherence. Black holes push this mode of reasoning to its extreme. They demand that physics trust its deepest principles even when direct verification is impossible. This reliance on internal consistency raises philosophical questions about scientific realism. Are unobservable structures like replica wormholes real? Does it matter? From a pragmatic standpoint, reality is defined by explanatory power and consistency. If a concept plays an indispensable role in a theory that accurately describes the universe, then it earns a form of reality, even if it cannot be directly observed. The information paradox has expanded this notion of reality. It suggests that some elements of the universe are real not because we can see them, but because without them the universe would not make sense. This has implications beyond black holes. It affects how physicists think about the early universe, quantum gravity, and even the foundations of quantum mechanics. The idea that reality is structured by information rather than objects is gaining traction across multiple fields. Black holes serve as the proving ground for this idea because they compress the universe's deepest issues into a single phenomenon. Another consequence of the paradox is how it reframes the meaning of disappearance. In everyday language, to disappear means to cease to exist. In physics, disappearance often means something subtler, to become inaccessible, delocalized, or transformed beyond recognition. Black holes force physics to adopt this subtler meaning. An object falling into a black hole does not vanish. Its information becomes distributed across degrees of freedom that no longer resemble the object. Identity dissolves, but existence persists. This challenges deeply human intuitions about persistence and loss. It suggests that the universe does not operate in terms of objects and endings, but in terms of transformations and encodings. What looks like destruction at one level is preservation at another. The information paradox thus becomes a lesson in humility. It shows that human categories, inside, outside, here, gone, are approximations. They work well at everyday scales, but they break down at the extremes. Physics advances by recognizing when its language has outlived its usefulness. Black holes mark such a boundary. They force physics to replace object-based thinking with process-based thinking. Reality becomes something that happens, not something that simply is. This shift has consequences for how we think about the future of physics. If space-time is emergent, then a complete theory of quantum gravity may not look like a theory of geometry at all. It may look like a theory of information processing, where space and time arise as effective descriptions. Black holes are the clearest hints of this future theory. They show that when information density becomes extreme, geometry loses its autonomy. It bends, dissolves, and reconfigures to preserve deeper laws. In this sense, black holes are not failures of space-time. They are demonstrations of what space-time really is. The information paradox has transformed from a threat into a guide. It no longer asks whether physics is inconsistent. It asks which assumptions must be revised to reveal a deeper consistency. As we move forward, this lesson becomes increasingly important. The next generation of theories will likely abandon many familiar concepts. They will speak in the language of entanglement, complexity, and information flow. Black holes will remain central to this effort. They will continue to challenge intuition, frustrate explanation, and reward patience, not because they hide answers, but because they reveal the limits of how answers can be framed. In the next part, we will explore how these ideas influence our understanding of reality itself, what it means for something to exist, for something to be lost, and for something to be known. When information, not space-time, sits at the foundation of the universe, because once black holes force us to rethink observation, they inevitably force us to rethink existence, and that may be their most profound contribution of all. As the black hole information paradox reshapes ideas about observation and knowledge, it inevitably reaches a deeper question *, what does it mean for something to exist * when information, not matter or space-time, is fundamental? In classical physics, existence is straightforward. An object exists if it occupies a position in space and persists through time. Its properties can be measured, tracked, and predicted. Even when an object is destroyed, its components remain somewhere in space-time. Black holes dismantle this simplicity. When an object crosses the event horizon, it no longer occupies a well-defined location in any space-time accessible to an external observer. Its internal structure is unmeasurable. Its future cannot be tracked in ordinary terms. Yet physics insists that its information still exists. This forces a separation between * existence as present * and * existence as encoding *. The object no longer exists as an object. It exists as a pattern in the quantum state of the universe. This is a profound shift. It suggests that existence is not tied to form or location, but to information. As long as information is preserved, existence persists, even if the original structure is irreversibly transformed. Black holes therefore introduce a new category of existence, one that is non-local, delocalized, and inaccessible, yet real. This category is not limited to black holes. In quantum mechanics, wave functions encode possibilities that do not correspond to definite objects until measured. Entangled states span regions of space without belonging to any one place. Virtual particles exist fleetingly without classical identity. Black holes push these quantum features to their extreme. They show that classical existence is an emergent concept, valid only when information is organized in stable, localized ways. When information density becomes too high, that organization dissolves. This has consequences for how identity is understood. An object falling into a black hole loses its distinguishing features almost immediately from the perspective of the outside universe. Its mass contributes to the black hole. Its charge and angular momentum may influence the exterior geometry. Everything else is erased from classical description. Yet information theory insists that those distinguishing features are not destroyed. They are encoded in correlations too complex to observe. This means identity is not fundamental either. Identity depends on accessibility. When information is accessible, identity persists. When information is inaccessible, identity dissolves, even if the information itself remains. This distinction matters when considering what it means to lose something. In everyday life, loss is defined by irretrievability. If you cannot recover something, it is gone. Physics draws a sharper line. Something is lost only if information is destroyed. Black holes demonstrate that these definitions do not align. From a human perspective, falling into a black hole is absolute loss. From a fundamental perspective, it is transformation without erasure. This mismatch between perspectives is not a paradox. It is a consequence of scale. Human experience is limited to coarse-grained information. Fundamental physics operates at fine-grained levels beyond direct access. The two descriptions cannot be reconciled into a single narrative without contradiction. Black holes force physics to accept that reality may not be narratable in human terms at all scales. This acceptance changes how questions are framed. Instead of asking where did it go, physics asks how is it encoded. Instead of asking does it still exist, physics asks is information preserved. These questions are less intuitive but more precise. They also alter how endings are understood. A black hole evaporation looks like an ending. The black hole disappears. Nothing remains but radiation. Classical intuition says this is destruction. Information theory says it is redistribution. The universe does not end things. It rearranges them. This perspective aligns black hole physics with a broader pattern in nature. Stars do not vanish when they explode. They scatter their elements. Living organisms do not disappear when they die. Their matter and energy disperse. Black holes extend this pattern to information itself. What makes black holes special is not that they destroy, but that they scramble. They scramble so thoroughly that recovery becomes practically impossible, even though preservation is exact. This introduces an important distinction between practical irreversibility and fundamental reversibility. At the deepest level, the universe may be reversible. At the level of experience, it is not. Black holes sit precisely at this divide. They preserve reversibility in principle while enforcing irreversibility in practice. This is why they feel so final, even though physics says they are not. The information paradox forced physicists to confront this divide explicitly. It revealed that irreversibility is not a basic feature of the laws of physics. It emerges from complexity. Once complexity crosses a certain threshold, reconstruction becomes impossible for any realistic observer. Black holes represent the ultimate expression of this threshold. This has implications for the future of the universe. If information is always preserved, then the universe never truly forgets. Even as stars burn out and black holes evaporate, the quantum state of the universe retains a complete record of its history, but that record becomes increasingly scrambled. The far future of the universe may contain all the information of the past, but in a form so diffuse and complex that no structure resembling memory, identity, or causality remains. This challenges common intuitions about cosmic death. The universe does not end with a clean erasure. It ends with maximal dispersal of information. Black holes accelerate this process. They act as engines of complexity, rapidly converting structured information into nearly inaccessible forms. In this sense, black holes are not anomalies. They are natural outcomes of a universe governed by gravity and quantum mechanics. They show what happens when information density and gravitational collapse intersect. The information paradox also reframes the relationship between physics and meaning. Physics traditionally seeks explanations that reduce phenomena to simpler components. Black holes resist this reduction. They do not simplify. They compress complexity into irreducible entanglement. This suggests that some aspects of reality cannot be fully understood through decomposition. They require holistic descriptions. The paradox, therefore, pushes physics toward a more relational view of reality. Entities are defined not by intrinsic properties, but by their relations and correlations. This view aligns with developments in quantum information theory, where systems are characterized by how they are entangled rather than by what they are made of. Black holes are extreme relational systems. Everything about them is defined by how information is connected, scrambled, and redistributed. This relational perspective also affects how causation is understood. In classical physics, causes precede effects in a clear chain. In quantum systems, causation is more subtle. Correlations exist that do not map neatly onto causal sequences. Black holes operate in this regime. The information that emerges in Hawking radiation is correlated with the past, but not in a way that allows tracing a simple causal path. The cause exists, but it is spread across the entire system. This challenges the idea that understanding requires tracing linear causes. Sometimes understanding means accepting that causation is distributed. The information paradox thus becomes a lesson in epistemic humility. It teaches that the universe may obey strict laws while remaining opaque to localized understanding. That preservation of information does not guarantee preservation of meaning. That existence does not guarantee accessibility. Black holes embody all of these lessons. They show that physics can be complete without being comforting. That consistency does not imply clarity. That truth may exist beyond narrative. As this perspective settles, it reshapes the goal of physics itself. The goal is no longer to produce a single unified picture that explains everything in intuitive terms. The goal is to produce a framework that is internally consistent, empirically grounded, and honest about its limits. The black hole information paradox has forced physics to move in this direction. It has transformed from a crisis into a compass. It points toward a future where reality is understood not as a collection of objects in space, but as a vast, evolving structure of information. In that future, black holes will not be seen as places where things disappear. They will be seen as places where the universe reveals how deeply it values information, and how little it cares whether that information remains comprehensible to those who try to observe it. As the black hole information paradox reaches this depth, it begins to alter not just physics, but the expectations we place on explanation itself. By now, it is clear that the paradox was never simply asking whether objects disappear. It was asking whether reality is obligated to remain intelligible at all scales. Black holes suggest that it is not. They show that the universe can be perfectly lawful while remaining permanently opaque to localized understanding. The laws operate without contradiction. Information is preserved. Evolution is unitary. And yet, for any observer bound by finite resources, finite time, and finite access, vast portions of reality remain unreachable in practice. This realization forces a recalibration of what explanation means. In everyday science, explanation implies compression. We take complex phenomena and reduce them to simpler rules. We trade detail for understanding. This works extraordinarily well in most domains. Black holes resist compression. The information they scramble cannot be summarized into a simpler description without losing essential content. The complexity is not incidental. It is fundamental. This suggests that explanation has limits not because of ignorance, but because of irreducible complexity. Some systems may be fully governed by simple laws, yet produce outcomes that cannot be simplified without distortion. Black holes appear to be such systems. The information paradox taught physics that knowing the laws is not the same as being able to reconstruct outcomes. The universe may be fully deterministic and still functionally unpredictable. This distinction matters deeply. It separates ontological order, epistemic access. The universe may be ordered at its core, even if no observer can fully decode that order. Black holes sit precisely at this separation. They preserve order in principle while destroying it in practice. This also reframes the meaning of disappearance. When an object falls into a black hole, it disappears from every practical description. No observer can retrieve it. No experiment can recover its structure. No narrative can follow it. Yet at the deepest level, nothing has been erased. The paradox forces physics to accept that disappearance is observer relative. It is not a fundamental property of reality. It is a property of access. This realization is uncomfortable because human intuition is built on access. What we cannot access feels unreal. Black holes demonstrate that this intuition fails at cosmic extremes. The universe does not prioritize observers, it prioritizes consistency. If preserving information requires sacrificing accessibility, the universe does so without hesitation. This perspective also reshapes how we think about finality. Black holes have long been associated with ultimate endings, points of no return, cosmic death traps, absolute erasure. The information paradox strips them of this symbolic role. They are not ends, they are transitions. They take structured information and convert it into highly scrambled forms. They do not terminate processes, they accelerate them toward complexity. In this sense, black holes are engines of transformation, not destruction. This has implications for the fate of the universe itself. If information is never destroyed, then the universe never truly forgets its past. Even as stars die, galaxies disperse, and black holes evaporate, the full quantum state retains a record of everything that ever happened. But that record becomes increasingly encoded in correlations too complex to reconstruct. The far future of the universe may contain all the information of its history, but none of its stories. Memory, identity, and causality may dissolve, even as information remains. Black holes push the universe in this direction faster than any other process. They are not anomalies in cosmic evolution. They are accelerators of its deepest trend, the growth of complexity. This perspective also reframes entropy. Entropy is often described as disorder. In the context of black holes, it is better described as inaccessibility. As entropy increases, information becomes harder to extract. The number of microstates grows. Reconstruction becomes impossible. Black hole entropy is enormous because black holes maximize inaccessibility. They hide information behind horizons, then release it in scrambled radiation. The page curve tracks this process precisely. Early on, information is hidden. Later, it is released, but only in a form that cannot be decoded by any realistic observer. This resolves the paradox without restoring comfort. The universe remains lawful, but not narratable. This realization also has consequences for the idea of a complete theory of physics. A complete theory may not give us a complete picture in the human sense. It may describe reality accurately while remaining opaque. It may explain why things cannot be explained further. This is a subtle but crucial shift. Completion no longer means total clarity, it means internal consistency and correct limits. The black hole information paradox teaches that knowing where explanation ends is as important as knowing where it begins. This lesson applies beyond black holes. It applies to the early universe, where initial conditions may never be fully reconstructible. It applies to quantum measurement, where outcomes are probabilistic and irreducible. It applies to complexity, where simple rules generate behaviors that cannot be summarized. Black holes simply force us to confront this lesson directly. They compress all these issues into a single object and refuse to let us look away. The paradox also reframes the role of philosophy in physics. For much of the 20th century, philosophy was treated as secondary, useful for interpretation, but not essential. The information paradox reversed this hierarchy. Resolving it required careful thinking about what information is, what existence means, and what it means for laws to be fundamental. These are not technical questions, they are conceptual ones. The progress made did not come from better telescopes or faster computers alone, it came from re-examining assumptions that had been taken for granted. Black holes forced physics to become reflective. This reflection has changed the language of the field. Physicists now speak fluently about entanglement, complexity, and information as fundamental ingredients. Geometry has become something to be explained, not assumed. This is a profound transformation. It suggests that the next major breakthroughs in physics may not come from discovering new particles or forces, but from understanding how information organizes reality. Black holes are the testing ground for this understanding. They show that when information density becomes extreme, familiar categories collapse. Inside and outside blur, past and future lose clarity. Objects dissolve into correlations. Yet nothing breaks. The laws remain intact. This is perhaps the most unsettling lesson of all. Reality can remain perfectly consistent while becoming deeply alien to intuition. The black hole information paradox does not reassure us that the universe is simple or comprehensible. It reassures us that it is coherent, even when it is incomprehensible. That distinction matters. It means physics does not promise comfort, it promises consistency. And consistency is enough to build understanding, even when understanding cannot be turned into a story we can easily tell. As this journey continues, one conclusion becomes unavoidable. Objects do not truly disappear in black holes, but neither do they remain as objects. They are transformed into something that no longer fits human categories, something that exists without form, without location, and without narrative. That is the price of preserving information at all costs, and the universe appears perfectly willing to pay it. As the black hole information paradox unfolds towards its final implications, it reveals something that goes beyond physics and into the structure of explanation itself. What began as a technical contradiction between general relativity and quantum mechanics has become a lesson about the limits of human understanding when confronted with a universe that does not organize itself around intuition. At this stage, the paradox no longer asks whether information is lost. That question has been answered with increasing confidence. Information is preserved. The deeper question now is what preservation actually means in a universe where structure, identity, and narrative are not fundamental. Black holes demonstrate that preservation does not imply continuity of form. An object falling into a black hole does not retain its shape, composition, or individuality in any recognizable sense. Its atoms do not remain atoms. Its internal order does not survive. What persists is only the abstract pattern encoded in quantum correlations. This forces a reconsideration of what it means for something to continue existing. In everyday terms, existence is tied to stability. A thing exists if it maintains coherence through time. Black holes show that coherence is optional. Existence can persist even when coherence dissolves. This idea is difficult to accept because human cognition relies on stable patterns. We recognize things because they persist. When persistence ends, we interpret that as disappearance. Black holes expose this bias. They reveal that disappearance is not a fundamental concept, it is a psychological one. Physics operates at a level where transformation does not require preservation of identity. This realization shifts the paradox from physics into metaphysics. It suggests that identity is emergent, not intrinsic. It exists only when information is organized in ways that allow recognition and tracking. When organization collapses, identity dissolves, even though information remains. The black hole is therefore not a destroyer of existence. It is a destroyer of asterisk recognizability. This distinction matters deeply for how we interpret the universe. It suggests that the universe is not built from objects but from processes. Objects are stable processes that persist long enough to be named. When stability fails, processes continue without names. Black holes are regions where naming breaks down. From this perspective, the information paradox becomes a statement about the limits of language. The words we use, inside, outside, object, loss, stop corresponding cleanly to reality. Physics does not fail when language fails. Language fails because it evolved for a different scale of reality. Black holes force physics to operate without linguistic comfort. This also reshapes how causation is understood. In classical thinking, causes produce effects in a linear sequence. A thing falls into a black hole, therefore it is gone. This chain assumes that effects must resemble causes in recognizable ways. Information theory rejects this assumption. A cause can produce an effect that bears no structural resemblance to it, as long as information is preserved. The relationship is not one of similarity, but of correlation. Black holes demonstrate this brutally. The Hawking radiation emitted late in a black hole's life does not resemble the objects that formed it. There is no echo of shape, substance, or history, yet the information is encoded. Cause and effect remain linked, but not narratively. This breaks a deep expectation about explanation. That understanding means tracing recognizable chains. Black holes show that understanding may require accepting chains that cannot be visualized. The paradox also reframes the role of horizons. Event horizons are often described as physical boundaries. In the information theoretic view, they are better understood as asterisk boundaries of description status. They mark where one effective description gives way to another. For an external observer, the horizon is a surface where information appears to freeze and thermalize. For an infalling observer, it is nothing special. Both descriptions are valid within their own regimes. This duality does not imply contradiction. It implies that reality admits multiple, incompatible descriptions that cannot be unified into a single picture. This is not a failure of physics, it is a structural feature of quantum systems. Wave-particle duality already demonstrated this at small scales. Black holes extend it to space-time itself. The information paradox therefore teaches that the demand for a single global description may be misguided. Nature may not provide one. Instead, it provides asterisk consistency across perspectives, not consistency within a single narrative. This lesson has consequences for how future theories are constructed. A theory of quantum gravity may not describe what really happens in a pictorial sense. It may describe how different descriptions remain mutually consistent without collapsing into contradiction. This is a different standard of explanation. It prioritizes coherence over visualization. Black holes force physics to adopt this standard. They also challenge the role of intuition. Much of physics progressed by refining intuition, training it to handle relativity, quantum mechanics, and curved spacetime. The information paradox suggests there may be limits to this strategy. Some aspects of reality may never become intuitive, not because we lack imagination, but because intuition evolved to handle environments where information is accessible and objects persist. Black holes violate both conditions. This does not mean physics becomes meaningless. It means physics becomes abstract in a deeper sense. Abstraction is not a weakness, it is how science operates when intuition fails. The black hole information paradox marks the point where physics must fully embrace abstraction as unavoidable. This embrace has already reshaped the field. Concepts like quantum error correction, complexity, and entanglement entropy now play central roles in understanding space-time. These are not geometric concepts, they are informational ones. Space-time emerges as a code. Black holes are regions where that code becomes maximally dense and maximally scrambled. This coding perspective also clarifies why black holes are so effective at hiding information. They behave like optimal encoders. They spread information across degrees of freedom in ways that minimize accessibility. From an information theoretic standpoint, black holes are not pathological, they are efficient. This reframes their role in the universe. They are not mistakes. They are natural consequences of gravity and quantum mechanics interacting under extreme conditions. Their existence does not threaten the laws of physics, it reveals their deepest structure. The information paradox also clarifies why attempts to recover information from black holes are futile in practice. Even if the information is preserved, decoding it would require controlling an astronomical number of degrees of freedom with perfect precision. This is not just technologically impossible, it is physically implausible. The universe preserves information, but it does not guarantee accessibility. This distinction may apply far beyond black holes. There may be many processes in the universe where information is preserved in principle but lost in practice. Black holes are simply the most dramatic example. Recognizing this changes how loss is interpreted. Loss becomes contextual, not absolute. From the perspective of the universe, nothing is lost. From the perspective of observers, almost everything is. This duality is not a contradiction, it is a reflection of scale. As the paradox approaches its philosophical resolution, it becomes clear that it was never about black holes alone. It was about whether reality is obligated to remain interpretable by beings embedded within it. The answer appears to be no. It remains consistent. It preserves information. But it does not preserve meaning, identity, or narrative in any observer-centered way. Black holes expose this truth. They show that the universe operates according to principles that do not prioritize comprehension. Comprehension is a local, emergent phenomenon. Physics must respect this. In doing so, it reaches a more mature understanding of its own limits. The black hole information paradox does not end with a neat solution. It ends with a reframing of what solutions are allowed to look like. Not every paradox resolves into clarity. Some resolve into structure. Black holes provide such a resolution. They leave us with a universe that is consistent without being transparent, ordered without being simple, and complete without being fully knowable. And that may be the most honest picture physics can offer. As the black hole information paradox approaches its final conceptual horizon, it forces physics to confront a quiet but unavoidable conclusion. Asterisk knowledge itself is a physical phenomenon subject to the same limits and constraints as matter and energy. This realization did not arise from philosophy alone. It emerged from the technical struggle to preserve unitarity without destroying space-time. In doing so, physics discovered that what can be known, reconstructed, or accessed is not merely a matter of intelligence or technology. It is governed by deep physical laws. Black holes make this explicit. They are not just objects that test gravity. They are environments that actively regulate knowledge. They determine which information can be accessed, when it can be accessed, and in what form it can appear. This transforms the information paradox into a statement about astroscopistic physics data, the physics of knowledge itself. In classical science, knowledge is passive. The universe exists independently of what is known about it. Observation merely reveals what is already there. In quantum mechanics, this separation begins to erode. Measurement affects the system. Knowledge becomes participatory. Black holes push this even further. They show that the universe can preserve information while actively preventing it from being assembled into knowledge by any observer. The barrier is not ignorance, it is physical law. The event horizon is not merely a geometric surface, it is an epistemic boundary. Crossing it does not just change what can be seen, it changes what can be known. From outside the horizon, the black hole is described by a small set of macroscopic parameters. From inside, space-time appears continuous and locally normal. From the fundamental level, neither description is complete. This forces physics to acknowledge that asterisk knowledge is observer relative, not because reality changes, but because access changes. The information paradox thus undermines the idea of a view from nowhere, a single, complete description of reality independent of perspective. Instead, it suggests that reality admits multiple valid descriptions, each constrained by physical access. This idea echoes a deep principle already present in relativity. Simultaneity is observer-dependent. Black holes extend this dependence to information itself. What exists is not in question. What can be known is. This distinction reshapes the goal of explanation. Explanation is no longer the construction of a complete picture. It is the articulation of consistent relationships between perspectives. A theory succeeds not by collapsing viewpoints into one, but by showing why they do not contradict. Black holes require this kind of explanation. They force physics to give up the expectation of global transparency. The universe does not owe us a single coherent narrative that fits all observers simultaneously. Instead, it offers asterisk consistency across limits. This consistency is subtle. For an infalling observer, physics remains local and smooth at the horizon. For a distant observer, information is slowly encoded in radiation. For the underlying quantum state, neither description is fundamental. All three are correct within their domains. The information paradox dissolves only when physics accepts that no single description is privileged. This acceptance has consequences for how theories are evaluated. A theory that preserves unitarity but violates intuition may be preferable to one that preserves intuition but violates consistency. Black holes force physics to choose consistency over comfort. This choice has already reshaped the standards of explanation in fundamental physics. The success of holography and quantum error correction models suggests that space-time is not a primitive ingredient. It is a derived one, emerging from patterns of entanglement. If space-time is derived, then the notion of inside a black hole is also derived. The interior is not a separate region of fundamental reality. It is a way of organizing information that is meaningful only in certain descriptions. This reframes one of the most emotionally charged questions in black hole physics. What happens to something that falls in? From the perspective of fundamental laws, nothing special happens. Information is preserved, evolution is unitary. The system evolves according to the same rules as everything else. From the perspective of an observer, something dramatic happens. The object disappears forever from accessible reality. These statements are not contradictory, they are statements about different layers of description. Black holes thus force physics to distinguish between asterisk ontic reality, what exists, and asterisk epistemic reality, what can be known. This distinction is not philosophical decoration, it is required for consistency. Ignoring it leads directly to paradox. The information paradox arose because physicists implicitly assumed that ontic and epistemic reality must align. Black holes demonstrate that they need not. The universe may preserve information in ways that permanently exceed epistemic access. This insight has implications far beyond black holes. It affects how we think about the early universe, where initial conditions may never be fully reconstructible. It affects how we think about quantum measurement, where outcomes are probabilistic and irreversible. It affects how we think about complexity, where simple laws generate behaviors that cannot be compressed. Black holes are simply the most extreme case. They expose the difference between asterisk lawful evolution time and asterisk knowable evolution time. This difference also clarifies why the information paradox felt so threatening. Physics had long assumed that preserving information meant preserving reconstructibility. Black holes show that this assumption was never guaranteed. Preservation does not imply retrievability. Once this is accepted, the paradox loses its sting. Information can be preserved without being accessible. Unitarity can hold without enabling reconstruction. Consistency can exist without transparency. This realization also reframes the role of observers in physics. Observers are not passive recorders of reality. They are physical systems subject to constraints. Their ability to acquire, store, and process information is limited by the same laws that govern everything else. Black holes highlight this limitation dramatically. No observer, no matter how advanced, can bypass the constraints imposed by horizons, complexity, and entanglement. This does not make observers irrelevant, it makes them contextual. Physics must describe not only what exists, but what exists relative to an observer's access. This is not relativism, it is precision. It recognizes that descriptions are tools, not mirrors. The black hole information paradox thus leads to a more mature view of science, one that does not equate understanding with visualization or accessibility. Understanding becomes the ability to state * what can be said, * what cannot be said, and * why. Black holes are exemplary in this regard. They show that some features of reality are structurally inaccessible, not accidentally hidden. No future technology will reveal them. No clever experiment will bypass the horizon. This does not make physics incomplete. It defines its scope. In this sense, the paradox does not end with a solution. It ends with a clarification of limits. Physics reaches a point where further questions are not meaningless, but unanswerable in principle. Recognizing this boundary is itself a form of knowledge. Black holes mark such a boundary. They show that the universe is consistent without being fully legible. That information is preserved without being retrievable. That existence does not guarantee accessibility. These lessons are not comfortable, but they are honest. They force physics to abandon the fantasy of total comprehension and replace it with disciplined humility. This humility does not weaken science. It strengthens it. It prevents overreach. It guards against contradiction. It ensures that theories respect their own limits. The black hole information paradox is not a warning that physics is broken. It is a reminder that physics is embedded in the universe it describes, and therefore subject to the same constraints as everything else within it. Understanding is physical, knowledge is bounded, and black holes are the places where those bounds become impossible to ignore. As the black hole information paradox nears its deepest implications, it becomes clear that it is not merely a problem about black holes, nor even a problem about information. It is a problem about * what kind of universe we live in, and what kind of understanding that universe permits. For centuries, science advanced under an implicit promise that with enough knowledge, enough precision, and enough time, reality would become transparent. The black hole information paradox quietly withdraws that promise. It does not say reality is chaotic. It does not say the laws are inconsistent. It says something more unsettling. It says reality may be perfectly lawful and still fundamentally resistant to full disclosure. Black holes are the clearest expression of this resistance. They obey every known law of physics. They conserve energy, they conserve information, they follow unitary evolution, and yet they produce regions of reality that are permanently sealed off from reconstruction by any observer. This is not because observers are weak, it is because the universe enforces limits on intelligibility. The paradox teaches that intelligibility is not guaranteed by lawfulness. The universe can be internally consistent without being externally readable. This realization changes the role of explanation in physics. Explanation can no longer mean rendering everything accessible. It must instead mean mapping the boundaries of access. A successful explanation is one that clearly states not only what happens, but what cannot be recovered, and why. Black holes demand this kind of explanation. They do not hide information behind temporary barriers. They hide it behind horizons defined by the structure of space-time and the growth of complexity. These barriers are not technological, they are fundamental. Once information crosses certain thresholds of entanglement and dispersion, it ceases to be reconstructible in principle. This introduces a new category into physics, * information that exists without being knowable. This category had no place in classical science. Classical physics assumed that if something exists, it can in principle be observed. Black holes invalidate this assumption. They show that existence and observability can diverge permanently. This divergence has profound consequences for how we think about reality. It implies that the universe contains facts that are never facts for anyone, events that happen without leaving an interpretable trace, structures that exist without ever becoming objects of knowledge. This does not make them unreal, it makes them epistemically closed past them. Black holes create epistemically closed regions not by isolating matter, but by isolating correlations. The information is not localized, it is spread so thin across so many degrees of freedom that no observer can assemble it into a coherent picture. The paradox thus reframes the meaning of hidden. Hidden does not mean concealed behind a veil that can be lifted, it means dispersed beyond recovery. This kind of hiding is irreversible even in a unitary universe. The laws run backward in principle, but no physical process can reverse the dispersion. Black holes therefore reveal a crucial asymmetry between *fundamental reversibility and *practical irreversibility. At the deepest level, the universe may be reversible. At every level relevant to observers, it is not. This asymmetry is not accidental. It is the source of time's arrow, of entropy, of memory, and of meaning. Black holes intensify this asymmetry to its maximum. They take structured information and accelerate it towards maximal dispersion faster than any other known process. In doing so, they show that irreversibility does not require violation of laws. It emerges naturally from lawful evolution. This undermines a long-standing intuition that irreversibility implies destruction. Black holes show that irreversibility can arise from preservation. This insight reconciles thermodynamics with quantum mechanics in a new way. Entropy increases not because information is lost, but because it becomes inaccessible. The black hole information paradox forced physics to internalize this lesson. Once internalized, many apparent contradictions dissolve. The paradox only appears paradoxical if one assumes that preservation implies retrievability, that existence implies accessibility, and that explanation implies visualization. Black holes dismantle all three assumptions. They show that preservation does not imply retrievability, that existence does not imply accessibility, and that explanation does not imply visualization. This triad defines the modern understanding of the paradox. With this understanding, black holes cease to be threatening. They stop looking like violations of physics and start looking like demonstrations of its full consequences. They are not loopholes, they are extreme but lawful outcomes. This perspective also reframes the emotional weight often attached to black holes. They are frequently described as cosmic destroyers, ultimate endpoints, places where meaning collapses. The information paradox reveals a quieter truth. Black holes do not destroy meaning, they dissolve it. Meaning depends on structure, memory, and accessibility. When information becomes maximally scrambled, meaning cannot be reconstructed, even though nothing has been erased. This distinction is subtle but essential. It explains why black holes feel final even though they are not. From the universe's perspective, nothing ends. From the observer's perspective, everything does. This duality is not a contradiction. It is a difference in scale. The universe does not operate on the scale of narratives. Narratives are an emergent feature of limited access. Black holes expose this limit brutally. They show that narratives are local phenomena, dependent on stable structures and slow information flow. When those conditions fail, narrative collapses. Physics does not collapse with it. The black hole information paradox thus teaches that * narrative closure is not a physical requirement. * the universe does not need to tell stories that can be followed from beginning to end. It needs only to obey its laws. This realization changes how we think about the goal of physics. Physics is not the art of turning reality into a story. It is the discipline of identifying consistent structures and respecting their limits. Black holes are among the most consistent structures in nature and among the least narratable. That combination is not an accident. It reflects a universe that values coherence over comprehensibility. This is not a pessimistic conclusion. It is a realistic one. It acknowledges that human understanding is a local adaptation, not a universal entitlement. The black hole information paradox forced physics to confront this without compromise. It did so by refusing to resolve into either loss or chaos. Instead, it demanded a third category, preserved but inaccessible. Once this category is accepted, a wide range of puzzles become manageable. The interior of a black hole need not be visualized. The fate of infalling objects need not be narrated. The final state of evaporation need not resemble the initial state. Consistency replaces imagery. This shift also clarifies why black holes have become central to so many branches of theoretical physics. They are not interesting because they are exotic. They are interesting because they compress all the deepest issues, gravity, quantum mechanics, thermodynamics, information and knowledge, into a single phenomenon. They are where the universe stops pretending to be simple, and they are where physics learns how to proceed without simplicity. The information paradox did not weaken physics. It strengthened it by forcing it to abandon unjustified expectations. It taught physics that the universe is under no obligation to preserve our intuitions, our categories, or our narratives, only its laws. And those laws, when followed to their limits, lead to black holes, not as exceptions, but as confirmations. In the final part, we will step back and ask what all of this ultimately tells us about disappearance itself, whether anything truly disappears in the universe, or whether disappearance is simply the name we give to the moment when information crosses the boundary between what can be known and what must remain forever beyond reconstruction. At the end of this journey, the black hole information paradox leaves us with an answer that is both precise and unsettling. It does not resolve into a simple yes or no. It resolves into a redefinition of the question itself. Do objects truly disappear in black holes? At the level of fundamental laws, the answer is no. At the level of experience, the answer is effectively yes. And the distance between those two answers is where the deepest insight lies. The paradox began as a technical problem. It asked whether black holes violate quantum mechanics by destroying information. That question forced physics into a confrontation between its two most successful frameworks. For decades, the contradiction appeared irresolvable. What ultimately emerged was not a loophole, but a realization. The universe does not treat disappearance the way human intuition does. In human terms, something disappears when it can no longer be accessed, recovered, or recognized. In physical terms, something disappears only if information is destroyed. These two definitions are not the same. Black holes expose this mismatch with absolute clarity. When an object falls into a black hole, everything that made it recognizable, its shape, structure, history, and identity, rapidly dissolves from any accessible description. No observer outside the black hole can track it. No experiment can retrieve it. No narrative can follow it. By every practical standard, it is gone. Yet at the deepest level of physical law, nothing has been erased. The information that defined the object is preserved, encoded in correlations spread across the quantum state of the universe. Those correlations are not localized. They are not extractable. They do not resemble the object they came from, but they exist. This forces a separation between disappearance as experience, as erasure. Black holes destroy the first without violating the second. This distinction resolves the paradox, but it does not soften its implications. Instead, it sharpens them. It tells us that the universe is willing to preserve information at the cost of meaning, identity, and accessibility. It prioritizes consistency over comprehensibility. Black holes are not exceptions to the laws of physics. They are places where the laws are followed so completely that human categories break. What disappears in a black hole is not information. What disappears is form. What disappears is narrative. What disappears is the possibility of reconstruction. This realization reframes not only black holes, but the nature of loss itself. Loss, as humans understand it, is not a fundamental feature of reality. It is an emergent consequence of complexity and limited access. The universe does not lose things. It rearranges them into forms that cannot be reassembled. Black holes are simply the most extreme example of this process. They take structured information and convert it into maximal entanglement. They spread correlations so widely and so finely that no observer can ever reverse the process. The laws remain reversible in principle, but irreversibility becomes absolute in practice. This is why black holes feel final, not because they violate the laws of physics, but because they obey them too well. The information paradox also teaches a deeper lesson about explanation. For centuries, science progressed under the assumption that explanation meant reduction, breaking things into simpler pieces that could be visualized and understood. Black holes mark the limit of that strategy. They cannot be reduced into simpler stories without distortion. Their behavior is governed by simple laws, but their outcomes are irreducibly complex. Understanding them requires abandoning the demand for intuitive imagery. This is not a failure of science. It is the point where science becomes honest about its limits. The resolution of the information paradox did not restore a comforting picture of black holes. It replaced one illusion with another, deeper truth, that reality can be lawful without being narratable. The universe does not guarantee that what it preserves can be told as a story. This insight reaches far beyond black holes. It applies to the early universe, where initial conditions may never be fully reconstructible. It applies to quantum measurement, where outcomes are probabilistic and irreversible. It applies to complexity itself, where simple rules generate patterns that cannot be compressed. Black holes simply force us to confront this truth without escape. They are not cosmic mistakes. They are mirrors. They reflect the difference between how the universe operates and how beings within it expect it to operate. They show that physics is not obligated to protect intuition. They show that the deepest laws may preserve consistency while dissolving meaning. And they show that disappearance is not a fundamental act of destruction, but a transition across a boundary of knowability. When something falls into a black hole, it does not vanish from the universe. It vanishes from every description that can be assembled by an observer. This distinction matters because it changes how we think about endings. The universe does not end things cleanly. It does not erase, it disperses. It transforms structure into complexity until no path back remains. Black holes accelerate this process, but they do not invent it. They reveal that irreversibility is not a flaw in the laws of physics. It is a consequence of how information spreads. The black hole information paradox forced physics to internalize this lesson. In doing so, it transformed from a crisis into a guide. It taught physicists where their intuitions fail. It taught them which assumptions were never guaranteed. It taught them how to distinguish between preservation and accessibility. And in the end, it taught them something uncomfortable but essential, that the universe does not exist to be understood in full. It exists to obey its laws. Understanding is something that happens locally, temporarily, and imperfectly. Where information remains organized enough to be recognized, black holes are places where that organization collapses completely. They do not mark the end of physics. They mark the edge of what explanation can look like. So, do objects truly disappear in black holes? No, nothing fundamental is erased. Yes, everything that made them an object is gone, and between those two truths lies the real answer. Disappearance is not the destruction of information. It is the moment when information crosses the boundary between what can be known and what must remain forever beyond reconstruction. Black holes are the universe's clearest expression of that boundary. Not as an error, not as an exception, but as a reminder that reality can remain perfectly consistent even when it no longer makes sense to us.